Alright, this time we're going to be looking at the idea of work. This is straight out of Chapter 7, the first section, and titled Work Done by a Constant Force, 7-1. But just the basic idea of work. And this is, like many things in physics, different than our everyday definition of the word work. Here, in physics, when we use the word work, we're actually referring to something very specific. And it turns out that when a force is applied to an object and that object moves through a given distance, then if you multiply those two values, you end up calculating the work done. With a certain caveat here, the force, which has a particular direction to it, and the displacement or distance traveled while that force is applied also has a direction to it. The directions of these must be the same if we're going to use just a general simple equation like this. Work is considered a scalar quantity, not a vector quantity. So even though force has a direction, a force could be this way, any direction you sort of need or think about, and also your distance or displacement again can be whatever direction. Each one has a direction. When you multiply them together, there is no direction to your answer. So work does not have a particular direction. It's a scalar quantity, not a vector quantity. When we end up doing this, well, the units of force we know are newtons, and the units of distance or displacement will typically be, try that again, meters. All right, well, what does this end up becoming? Well, we know what a newton is. A newton is a kilogram meter per second squared. And if we're going to multiply by a distance, then that's going to give us kilogram meter squared per second squared. And much like we did with units of force, kilogram meters per second squared, here we get to simplify this and call this something else. And it turns out the units of work are something called joules. Actually, if you have 1 kilogram meter squared per second squared, then what you have is 1 joule. Capital J if you shorten it, or lowercase if you write out the word. And so nice convenient unit to use. And just remember that we have force times distance. Okay, fair enough. Let's look at an example of this. This is going to be page 2, just for reference. We have a surface here, and just for argument's sake, let's say we have a smooth friction-free surface, and just we got a box sitting here. We're going to apply a force. Applied force, and let's call that 50 newtons. Okay. The mass of this object, well, let's call it M1. M1, we can give it a mass of 10 kilograms if you like. No big deal. But while we're applying this force, this object is going to move a given distance, and it's going to end up over here. There's our distance. All right, so how much work will we do? Well, if our distance is, let's say, 3.3 meters, then all we need to do to find the work done, since we know the force and the distance traveled are in the same direction, that's clear here in our setup, the work done with a capital W is equal to force times distance. So I have a force of 50 newtons. Multiply that by 3.3 meters. Handy dandy calculator. 165 joules of work were done. Very straightforward. Okay. Well, what if we have a situation where the force that we're applying to the object and the distance traveled are not in the same direction? So we can look at the same situation. We have our box sitting on the smooth surface, and it's going to travel. Let's say we push it across the floor that same distance, 3.3 meters. Okie dokie. Well, now, so the box will end up here. What if we are applying a force at an angle like this? So here's our force. And we're going to say, well, let's apply the same 50 Newton force. But this force is at an angle with the horizontal angle theta. And let's say, let's call angle theta 38 degrees. All right, so what do we have to do? Well, we have to realize that if we're going to look for the work is force times distance, and they must be in the same direction. This force actually does have a component that is parallel to this distance traveled. And if you just think about the x and y components of this force, or the horizontal and vertical if you prefer, you have a horizontal component here, and you have a vertical component here. Vertical component is in the downward direction. All right, so it's actually the horizontal component we are interested in. What would the value of that horizontal component be? The hypotenuse here, that is our 50 Newton force. I'm going to look at that over here, a little larger. This guy, there's our 50 Newton force there. This guy is going to be, here's theta, and remember theta is 38 degrees. This is the adjacent side to that angle, so this is going to be force of 50 newtons multiplied by cosine of theta. That is the value of the horizontal component of our applied force. So what I have to do is use that component of our applied force when I want to calculate the work that I do. So the work, when the force is not parallel to that distance, simply requires that I find the component of our force that is parallel to this. So the equation becomes force times cosine theta times distance. And in your textbook, this is often going to look just a little different, just rearrange a bit. Force times distance, and they move the cosine theta to the outside here, to the end. And that'll get you the work done when your force and your distance are not parallel. So what would it become here? Okay, well, the force was 50 newtons. Our distance was 3.3. And that was 165 in the previous example. Here we also have multiplied by cosine of 38 degrees. Turns out to be roughly 130 newtons. And so we still have a way to work with this, even though the force is not applied parallel to our distance. We simply must find the component of our force that is parallel to our distance traveled. And we will use that component to calculate the work done. There's an implication here. The implication is that the component of the force that is perpendicular to the distance traveled does no work. And that's actually true. So it's important and worth noting that any force or force component perpendicular to the distance traveled. I'll keep writing this over here. Produces zero work. Any force or component of a force that is perpendicular to the distance traveled produces zero work. Only a force parallel or a component of a force parallel to the distance traveled will produce some work. Thanks for watching. We're going to expand on this in the next video.